Okay, so this second example says
I'm not ready for this.
29.28 milliliters. So I'm going to try to write everything out. 29.28 milliliters of
God, I'm already messing up.
0.1032 molar acetic acid. Acetic acid is what kind of acid?
Weak acid.
Weak acid. Label, label, label. Is titrated to the equivalence point. It already tells us we are at the equivalence point. So there's no guessing involved now. With 25 milliliters of aqueous sodium hydroxide. Okay, so all we know is that we have 25 milliliters of NaOH. We don't know what the concentration is, but NaOH, label, strong base. And we know that we're at the equivalence point. That's so helpful because what's true at the equivalence point?
Moles of acid equals moles of base.
Moles of acid equal our moles of base. So, that's helpful. And then it says calculate the initial pH. So, before we worry about calculating like moles of base or anything, it just says calculate the initial pH. I would just read through the problem, kind of just get an idea for what it's asking you for. So we're going to be calculating the initial pH. We're going to be looking at the molarity of NaOH, what's the pH at the equivalence point, sketch the titration curve, and then pick the indicator. So not quite as much as the first example because we already know that we're at the equivalence point. The difference between this one and the one before was we were adding sodium hydroxide and we didn't know where we were in the titration. Now we know where we are. So the first thing we need to do is calculate the initial pH. So initial pH. I'm going to give you a little hint. More often than not, if it's a weak, strong titration, the weak is in the beaker. The strong is in the burette. So when you guys titrate Tuesday and Wednesday, you're going to do a strong, strong titration, and you're going to do a strong, weak titration. You're going to be using HCl and NaOH for the strong, strong, and you're going to be using NaOH and acetic acid for the strong, weak. Your acid is going to be in the beaker both times. Okay, so especially when it's the weak acid, it's in the beaker. So when we're looking at initial pH, we're going to be looking at it of the weak acid. So, acetic acid is a weak acid. What does it mean if it's a weak acid? It doesn't dissociate completely, which means when we add it to water, it's at equilibrium. First thing to always do is, let's just write an equation, whether it's strong or weak, because then that helps us, because if it's strong, it dissociates completely. And your entire concentration of your strong acid is also your concentration of your H+. Weak, not quite so lucky. What are my two products when my weak acid partially ionizes or partially dissociates? Okay, so I heard H3O plus and I heard C2H3O2 minus. So hydronium, and again, H3O plus is the same as H plus. And then your acetate ion. Just bringing stuff back from the last chapter. This is the weak acid. What is this? Conjugate base. That's going to be the big thing. Water really doesn't. So weak acid and its conjugate base. And what kind of base is this conjugate base? Weak base, because it comes from a weak acid. So acetic acid, and then we have acetate, which is the conjugate base. So if I need to find the initial pH of this, just like before, you use an ice table. Just like we did before. Initial pH of a weak acid, we need to find our H+, but it doesn't ionize completely, so we have to look at it at equilibrium. What's my initial concentration of my acetic acid? 0.1032. Don't worry about water. We don't have any H+ or acetate ions. Whenever you're solving for pH, You always are going to use X's, right, if we haven't figured that out. Because if we're solving for pH, we need to know H+. What else do we need to know in order to solve for X? Ka. You guys remember what the Ka of acetic acid is? Remember when I said you're going to be using this Ka all the time? You will probably have it memorized. Told you. So let's plug this in. Ka. Again, I'm skipping steps just to save some space. Write your Ka with your formulas first, just to get in the habit. So H3O plus times C2H3O2 minus over HC2H3O2. But to save space, here's what I have. What can I do to make life easy? Assume X is small. Don't forget to write that out. That gets rid of this X on the bottom. Okay, now multiply, take the square root, solve for X. So take a second, solve for X, check with people around you, see if you get something similar to each other. And then label what X is. Label what X is. What does X represent? Make sure you label it.
Do you please use 01 or something? Mine's 0136.
Yeah, that's fine.
Yeah.
So I got 0.00136 molar, and X is H plus.
Thank you.
Nice
Okay,
catch.
so here's X, and X represents H plus. How do I find the pH now? Negative log. Negative log 0.00136. And what do we get for our pH?
2.87.
.87. So our initial pH of our acid is 2.87. I'm going to write it up here just so when we draw the titration curve, it's easy for us to look back. Okay, questions on this first part? So then the second part says, what's the molarity of NaOH? So what do we need to find molarity? Moles and liters. Well, if you look at NaOH right now, we have 25 milliliters. What do we need? But what's true at the equivalence point? Moles of acid equal moles of base. So right now, use acetic acid's information and find moles of acid. Okay, so to find moles of acid, we're just going to use our concentration, 1032. And then what is that volume of acid in liters? 0.02928. So how many moles of acid is that? 0.00302 moles of acid. So how many moles of base do we have? Yeah, the same amount, right? Because we're at the equivalence point. That's the key thing here. So when they said we are at the equivalence point, that's why I wrote this right away. Because if we're at the equivalence point, moles of acid equal moles of base. So now I have moles of NaOH. What else do I need to use to find molarity? Liters. How many liters of NaOH do we use? Which is how many liters? So find that concentration. So what is the concentration of NaOH?
0.1208.
0.121 molar. Alright, so again, concentration of NaOH isn't going to change, so you just need moles, you need liters. We already knew our volume, so we just needed to figure out moles. And because we're at the equivalence point, moles of acid equal moles of base. So then it says, what is the pH of the solution at the equivalence point? Okay. Now is the long part.
Is that all step one?
So,
What?
pH at equivalence point.
This is no idea than
Here we
NaOH. This
go.
is the second one.
pH
Oh, gosh, now.
at equivalence point. So remember, at the equivalence point, the salt determines the pH, because this is a strong base, weak acid titration. So let's just think about it first, so we have an idea where we should see our pH. If it's a strong base, weak acid titration, where should our pH be, roughly, at the equivalence point? Above 7, right? Somewhere above 7, because strong wins. Strong base means at the equivalence point it's going to be basic, and that's because your salt is basic. You have a basic salt that you're forming at the equivalence point. So it's the same neutralization that we looked at in the last example, but we have acetic acid, sodium hydroxide, making water, and sodium acetate. Right, just a neutralization reaction here. At the equivalence point, we just solved for number of moles. We just determined at the equivalence point we have 0.00302 moles of acid and base. Now you don't necessarily have to write this part every time, because here's something that you can remember. At the equivalence point, moles of acid equal moles of base, which equals moles of what else? What else do we have? Salt. At the equivalence point, moles of acid equal moles of base, which also equals moles of salt. So we're writing this step every time. If you remember moles acid equal moles base equal moles of salt, you don't necessarily have to write this out, because you know at the equivalence point you have 0.00302 moles of salt. Okay, and again, your salt is what affects your pH, because you now have no more acid and no more base. These are used up completely. They completely neutralize each other at the equivalence point. That's the whole point of an equivalence point. A lot of points. So this is all that affects the pH at the equivalence point, and more specifically, which part of this salt is not neutral? The acetate. This is neutral. Na plus is neutral. The acetate is what affects pH. Again, because this is neutral, this is basic. Your salt is basic at the equivalence point for this titration, because you guys just told me that the pH at the equivalence point is above 7, because strong always wins. It's also because your salt is basic. So, let's take this, write the hydrolysis. So here are kind of the steps for calculating pH at the equivalence point. First thing, determine moles of salt. Right, at the equivalence point, we need to figure out how much salt do we have. How many moles of salt do we have? Second thing we need to do is write the hydrolysis reaction. And I know you guys loved that Texas lady so much. She actually has another video that's called Buffers Made Easy. And in that, I'm not as concerned about the actual buffers portion, but there is a section of the video where she actually goes through just writing hydrolysis reactions. So if you're like, I'm not super comfortable with it, over the long weekend, you can always go in. I have the link and the password on the lesson plan, so if you do need to go through, and I can be even more specific and put the time frame for the hydrolysis section. But all it is you're just going to write the hydrolysis reaction of the salt. Okay, the portion of the salt that is affecting pH. What is not neutral? That's what you're going to be writing. So, acetate, we said before, is the conjugate base of acetic acid. So hydrolysis means we add it to water. If acetate is a base, what is it going to do in this reaction? Accept an H and become acetic acid. And then what's water going to become? This is a base hydrolysis reaction. You're forming OH minus, which means if you write your equilibrium expression, this is for which K? Kb. This is a base. Ka is the ionization, the dissociation for an acid. This is not an acid. So you would be writing Kb. Make sure that you look at that every time you write an equilibrium expression. Because for this, they might only give you Ka. So we write the hydrolysis reaction of the salt. That's the next thing that we do. And then set up an ice table. So I guess step 3 for this,
I don't have enough room.
set up ice table. So in order to set up our ice table, what unit do we plug in?
Molarity.
Concentration molarity. So we need to know the molarity of this salt. Here's our number of moles. What else do we need to know to find molarity after the acid and the base are added together? Total volume. How much acid and base are added together at the equivalence point? Well, we already know that this is at the equivalence point. Here are our volumes. What is this total volume in liters?
0.05428.
0.0. Now we can find concentration. So we take our moles of salt, we take our total volume, because that's now, the salt is now in the total volume. And what is that concentration of salt? We do 0.00302 divided by the total volume. What do we get for concentration?
0.0556.
0.0556. And remember, initially all you have is the salt, because at the equivalence point, your acid and your base are used up completely. So all we have is the salt. Now we go through and set up an ice table like normal. Again, oops, I forgot my minus x. When we plug all of this into K, what K is it? KB. So we need to figure out KB for acetate. Well, we know Ka. What's the relationship between Ka and Kb? Equal Kw. We calculated this in the last one. So we get 5.56 times 10 to the negative 10 equals x squared. If I assume x is small, again, now I'm just saving some time. Not necessarily showing every step like I should, just to try to make time, make sure we get through everything. So multiply, take the square root. When we solve for x, what does x represent?
OH minus.
OH minus. So I got 5.56 times 10 to the negative 6. And that is OH minus. What will I find from OH minus?
POH.
The OH. So you just take the negative log. I got 5.26. What is that then? 7.4. The main steps for finding the pH at the equivalence point. Figure out your moles of salt. Write your hydrolysis reaction, your equilibrium, set up your ice table and solve, and then solve for pH. Okay, so now we figured out the initial pH, and we figured out the pH at the equivalence point. Now it wants us to sketch the titration curve. So this doesn't require any math, thank goodness. But we need titration. pH is always on the Y, volume added is on the X. To be even more specific, what were we adding in this titration?
NaOH.
NaOH. What was the initial pH for this titration? 2.87. So we're going to start at 2.87. Remember, we have this kind of curve because that's our buffer region. So whenever you have a weak, strong titration, you have this little curve because it's a buffer region. So here is my equivalence point. What's the pH at my equivalence point? 8.74. What volume of NaOH was added at the equivalence point?
25 milliliters.
Yep, 25 milliliters. And there's one more thing that we can put on here. Half equivalence point. So 12.5. How do we figure out the pH at the half equivalence point? pH equals pKa of the weak acid. So if the Ka of the weak acid is 1.8 times 10 to the negative fifth, take the negative log of that, you get 4.74. Okay, now last question says pick the best indicator. Again, we need the pH range of the indicator to make sure that it covers the pH at the equivalence point, 8.74. Again, like I said before, phenolphthalein has a range of 8 to 10. And so we will pick phenolphthalein.